close the door. You can unlock it here. Just put the hand on it. No, I haven't. Have y'all finished homework? No, sir. I didn't do it last time. Alright. So let's talk about series and parallel. When two components, yes, I have one question on the phone. It didn't show your work, but I think it's not working. You write the numbers. You write the formula. When two components are connected in series, the flow of current does not branch off. The same current that flows from one component is the same as the current that flows through the second. Yeah. This will be series and parallel. Most circuits are both series and parallel combinations. So the same current that flows through one component is the same as the current that flows through the other. So if we have two resistors in series, so if we connect two resistors in series, if 1 amp of current goes through the first, then 1 amp will go through the second. So if we have 1 amp of current going this way, there's nowhere for this current to go except through this one. So objects in series have the same current. For resistors, the total resistance of resistors connected in series is simply the sum of resistors. For example, have a 10 ohm resistor here and a 5 ohm resistor here. This is equal to a single resistor with 15 ohms. So the total resistance is equal to the sum of these two resistors. So to generalize this, let's suppose that we had several resistors connected in series. R1, R2, and R30. Then the total resistance would be equal to R1 plus R2 plus R3 and so on for how many you have. Series. Make sense? Keep your mask on, Michael. Pretty straightforward. You add a resistor in series, it's the same thing as adding the resistance value to that previous resistor. The current flowing through it will stay the same. Or I shouldn't say, the current flowing through the circuit or through each resistor is the same. You add resistance, current is going to go down because you're restricting the flow of electricity. But the same current will pass through all three. Make sense? Everyone good? So let's talk about in parallel. In parallel is more complicated than in series. In parallel, the current takes different paths. Hence, there's a branch. There may be different currents flowing through different components. Two components connected in parallel do not share the same flow of current. So let's do an example. Imagine we have a wire where we're sending, let's say, 3 amps of current, and we connect two resistors in parallel. 1 amp of current might go up this top branch, and 2 amps of current might take this bottom branch. They'll recombine together, and we get 3 amps of amps of current here. So if we had 3 amps of current, the current can split at a branch or node. We usually call these points here nodes. And some of the current, so we have 3 amps of current, the current is split at a branch, and we can have, for example, 1 amp of current take the top branch, and 2 amps of current take the bottom branch. Note the total current is constant. So if we have 3 amps in total, that 3 amps doesn't disappear, it just takes different paths. So the sum of the total current at this point is still 3 amps. We just have 1 amp of it going to the top, and 2 amps going to the bottom. And they can recombine together and stop tapping. And so in series, we have the same current. So the same current passes through, stop tapping. In series, we have the same current passing through all the resistors. Here, we have different currents, but what would you think would be still the same between them? So when components are in parallel, they have the same voltage drop. So the voltage across the components are the same. So let's look at our resistors. So let's suppose, same thing, we have a wire and branches. We have one resistor here, R1, have another resistor here, R2, and I have another resistor here I will call R3. And let's imagine that we were to continue this forever. then the total resistors, this is equal to a single resistor. The total resistance is equal to 1 divided by 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3 plus, and it repeats for how many resistors you had. So to give you a specific example, so this is the total resistance for parallel. So suppose we had So let's suppose that we have a 3 ohm resistor and a 6 ohm resistor. We can replace these two resistors with a single resistor. So let's look at our equation. The total, this is RT, the total resistance. The total resistance would be equal to 1 over 1 divided by 3 ohms plus 1 over 6 ohms. Plugging that into the calculator, making sure that we put parentheses around the denominator. We get 2 ohms. So this is equal to 2 ohms. So if we connect a 3 ohm resistor and a 6 ohm resistor, that's equivalent to a single resistor with 2 ohms. So connecting resistors in parallel, so connecting resistors in parallel reduces the total resistance, or reduces the resistance. So the total resistance is less than either resistor. Which makes sense. If you're having current flow through, so imagine this is a hallway. And let's say we have a lot of people rushing through the left hallway. We can reduce the flow of traffic by opening up the other hallway. Some people will go left, some people will go right, and now it's not as crowded as the hallway because there's multiple paths for you to take. Same thing for electrons. When we only have one resistor, 3 ohms, they have to push through this resistor. However, if we added another resistor, some of the electrons could go through this other path. So it reduces the total resistance. Guys, pay attention. John, hi John. So let's look at a circuit, a more complicated circuit. let's make up values for this. This would be 2 ohms, 3 ohms, this 4 ohms, this 5 ohms, this 6 ohms, and this 7 ohms. What is the total resistance of the circuit? So, when solving complicated circuits like this, you need to identify what is in parallel and what is in series. Note, some things are not as neither. For example, this is not in series with this resistor. It's also not in parallel. For it to be in parallel, both sides of the resistor must share the same wire. So if I were to look at these two resistors, we can see that they both use a green wire over here. And a red wire here. Thus, these two resistors are in parallel. Yeah. So these two are in parallel. Why are they a little louder? Yes. So these two are connected by a green wire. These two are connected by a red wire. So we can combine these two and into one resistor. The 3 ohm resistor and the 4 ohm resistor are in parallel and can be combined into one resistor. By the way, this is the most hardest thing we're going to do all year. You should really be paying attention as the next few homeworks are going to be over this. Yes, we will be doing this. So we can combine these, the total resistance for 3 ohm and 4 ohm is 1 divided by 1 divided by 3 ohm plus 1 divided by 4 ohm. So plugging that into the calculator. Yeah. That's equal to 1.714 ohm. So I can replace those two with a new resistor. So we can see that green wire is now, which was connected to the left side, and the red wire was connected to the right. Now collapsed, and we have this one resistor for it. We can do the same thing for these. These two are going to be in parallel. So if we look over here, we have matching wires on both sides. So these are in parallel. And then combining it together. Yes. So to combine 5 and 6, so we're going to combine 5 ohm and 6 ohm into a single resistor. And we use the parallel rule. 1 over 5 ohm plus 1 over 6 ohm, and that is equal to 2.7277 ohm. So we can redraw the circuit now. So we have a 2 ohm, a 1.7143 ohm, and we just saw that these two becomes the new one, 2.72727 ohm, and then the 7 ohm resistance. Yeah. These now are all in series. So you have these are now all in series. So we can just add those together. So the total resistance is 2 plus 1.714 plus 2.7277 plus 7. So the total resistance is equal to 13.441.558 ohms. So we can replace this entire circuit with a single resistor. another example. So let's do a simple one where we don't have to combine resistors. We have a 3-volt battery connected to half an ohm resistor. What is the current coming out of the battery? What is the current coming out of the battery? Current is equal to voltage over resistance. So the voltage is 3 volts. So it's 6 amps. Very simple, right? Alright, now let's do a slightly more complicated one. Let's say that we have 3 volts. We have 2 ohms. We have 1 ohm here. 2 ohms here. And 3 ohms here. Yeah, so 1, 2, 3, and then another 2 here. Now, what is the total current coming out of the battery? Is there any in parallel? So, which one will be in parallel? The 3 and 1. Do they share the same wires? So let me get color on the wires. So which ones did you say were in parallel? I didn't change anything. All I did was color it. So 3 and 2. Well, this has a red and a blue. This is a blue and orange. These are not parallel. 2 and 2. This is connected using a green, red and green. This is blue and orange, not parallel. There is no parallel. Put your mask on. Yes. Now let's see if there's anything in series. Is there anything in series? So if current were to go through this off branch, is there anywhere it splits off? So if a current is coming around here, is this the same current flowing through all these wires? Yes. So these are in series. So the current coming in here doesn't split off or branch. Components connected in series have no branches between their connections. So these are in series, and remember that for series, we simply add up all the resistors. So the total resistance of these will simply be 1 ohm plus 2 ohms plus 3 ohms, which gives us 6 ohms. So we can replace this with a 6 ohm resistor. So I'm just replacing this region right here. I can replace that region with a single resistor that has 6 ohms. Now then, let's relook at the circuit. Do these share the same wires? This is connected to both the same wire, and this terminal, this side, is connected to the same wire. So if both sides are connected with the same wires, they are in parallel. What? We replace, so these 3 resistors is the same thing as these 2. Or this one. All of these 3 is equal to this one resistor. So I connected it back into the circuit at these 2 points. So these 3 resistors have a total resistance of 6 ohms. So I can replace it, I can remove this portion and replace it with a single resistor equal to the sum of these. Since the off of both resistors uses the same wire, and the bottom of both resistors uses the same wire, they are in parallel and can be replaced with a single resistor. And the value of that resistor would be 1/2 ohms plus 1/6 ohms. And that would be equal to 1.5 ohms. I'm teaching. So these two resistors can be replaced, reconnecting it at these 2 points now. So reconnecting it at these 2 points with a single resistor has a value of 1.5 ohms. So we can now answer the original question. How much current is leaving the battery? We know current is equal to voltage over resistance. So the total voltage over the total resistance gives you the total current. The total voltage is 3 volts. The total resistance is 1.5 ohms. And thus the total current is 2 amps. Even though I'm color coding it, you need to be able to look at the circuit and tell without colors. So looking back at the original circuit, this wire and this wire is only used for the battery and these resistors. This one has a different wire here, so it's not in parallel, and this one uses a different wire here, so it's not in parallel with that resistor. However, if we look and imagine electrons moving, the same electron never diverges. There is no other path for the electron to go. So all of these share the same current. Same current means they're in series. We could have done it at any point. We could have recognized that these two were in series and replace it, connecting it right there. With a single resistor like this. And then we could have noticed that the same current is going through here, and then we can connect these in series. So it depends on whether or not you want to do all the series at once, or if you want to just do 2 resistors at the same time. Any questions? Or you need to be paying attention? You're constantly looking at your phone or wherever you're playing. Keep your mask on, Cody.